Picking up on some of the things I spoke about and John spoke about, dive in a little deeper into optics. And I'm going to focus on the 2/3 inch format, which is in the 3-chip, pretty much the center of the universe, for a couple of reasons. It's the biggest of the small format cameras. It's the only internationally standardized lens camera optical interface, which is a huge thing, by the way. Never been achieved before in video. And there are the smaller formats, of course, which are proliferating, and they're very important in the role that they play. But this is a good calibration of what we face with high definition. A high definition 2/3 inch, this is the size of the image on the imager that the lens is projecting onto the imager. It's 9+ millimeters by 5.4. And I've sliced it, you can slice it, dice it horizontally or vertically. I've broken it into millimeters vertically. And the whole issue is how many line pairs can I pump through 1 millimeter? That is our yardstick in optical measurements. In the lens camera, we look separately at resolution horizontally and vertically, primarily because there are different mechanisms going on in the vertical direction and the horizontal direction. Hopefully your lens is balanced both directions, but the camera can be different. And in the horizontal direction, it's the number of horizontal samples and that bandwidth issue, that digital filter that I spoke about. Now, looking closely at that 2/3 inch format, and we're going to put her onto a 1080 imager, which means we've got 1080 samples vertically. And Nyquist says if you've got 1080 samples vertically, you can resolve 540 line pairs per millimeter. It just so happens, and it is pure coincidence, that this is 5.4 millimeters. So it says if I've got 5.4 millimeters, I've got to resolve that. The lens has to transfer 100 line pairs per millimeter with high contrast. With high contrast, if that lens is to be sharp. And that's a hell of a challenge. John spoke about the 35 millimeter lenses being measured at 20 line pairs per millimeter, 25 perhaps, that they want the high contrast there. Because we've shrunk the image format down so much smaller than 35, the optical performance had to be pumped up. That took a decade to get to where we are today. When I say we, Canon, Fujinon, Angelo, all the Zeiss, the major manufacturers. Now, I've drawn here. I want to try and impress upon you what we're asking for here. I've drawn accurately 100 line pairs there. There is 100. You can count them if you want. Now, think about a millimeter. I got to get that through each millimeter at high contrast. At high contrast. Standard definition only has to get 44 line pairs per millimeter in a 2/3 inch image format. So those of you who have often asked the question, what really is the difference between a standard definition lens, 2/3 inch, and a high definition? I'm certainly asked that all the time, is huge difference. Totally different design. Because we're trying to get that through at picture center, 2.5 times more information at the same contrast as in a standard definition lens at high contrast. Now horizontally, if you dice it horizontally, that filter that's in all the cameras, in the high definition cameras, that 30 megahertz filter, is actually helping us. Here we only need 81 line pairs per millimeter horizontally. Still a lot. And for standard definition, 32 line pairs per millimeter. And again, just to give you a sense of the difference between the two, 2.7 times. No matter whether you look at it horizontally or vertically, it's 2.7 times more information has to be pumped through that tiny little millimeter. And a yardstick today, which I think is pretty amazing, any good 2/3 inch lens from any of your favorite optical manufacturers is going to deliver you about 60% MTF, 60% contrast at 100 line pairs per millimeter. That's pretty amazing. That's pretty amazing. And that is a typical profile. We limit out around the 200 line pairs. You can still see something. And that will give you a very sharp picture. And I'm sure you've all seen it. So now looking at the cameras themselves, the 3-chip camera, the prism, the chips mounted on it, the image-related circuits to read out, the ATD converter, the digital signal processing that we spoke about. Looking at the optical resolution, both horizontally and vertically, the 1920 by 1080 is very carefully chosen so that when you look at it in line pairs per picture height, line pairs per picture height, both dimensions, horizontal and vertical. Nyquist comes out at the same frequency, 540. That was by design. We tried to design a high-definition imaging system that had equality of resolution, what we call isotropic resolution. And typical curves from any of the major manufacturers today, 2/3 inch, 1920, 1080 cameras, the cameras have a profile something like this. In other words, they've got a very good curve in band, dropping down to maybe the 30–40% at Nyquist, and then there's some residual out there that they will deal with some filtering, etc. Now you put a lens on that with the 60% at Nyquist. I've actually drawn that a little higher there, but 60%, and you multiply the lens by these curves. This is what you actually get. And all of the cameras, each camera designer is wrestling between trying to maximize this curve and minimize this aliasing. And none of them publish anything. And what a Panasonic and a Sony and a Thompson and a Hitachi and all these camera manufacturers, Ikegami, nobody knows unless you measure. It is a very simple measurement. You can do it with test charts. And then you're going to find all of them will have their own criteria. They're all going to say, to some degree, I'm going to keep that curve high, and I'm going to live with a little bit of aliasing. Because happily, while a test chart can stimulate aliasing where you can see it, happily the real world, fine detail information in the world is rarely of a very high energy. And while it might stimulate aliasing, it's generally very small, to be generally, on most scenes, insignificant. So in summary, the tri-imager camera, the 3-chip camera, is essentially what we call a 444 system. The red and the green and the blue have that MTF characteristic, horizontally and vertical. They're all equal. That's good. That's very good. And there's a trade-off that's variable between manufacturers, and each will create their own pragmatic trade-offs. And actually, they've become very clever. The high-end 2/3 inch cameras certainly are quite clever. Now, let's take a snapshot just to show you what you're up against if you look at a chart. I picked two of the top-end cameras, the highest performing, Ikegami and a Sony. And I lifted out of the brochure their publication of specs on resolution. Iki gives 2 numbers. Sony gives 2 numbers. Whoops, they're the same. Yeah, no surprise. Pick Hitachi, pick Thompson, pick them all. You're going to find the numbers roughly there. Some might be 40, some are 45. Now, what's that telling you about the sharpness capability of that camera? By the way, they add a little thing in here which is implicit here, but they actually write it with a typical lens. And what they omitted to say is, I'll give you that number with a typical high-definition lens at picture center. At picture center. So it's a spot measurement. Now let's look at it. So they're giving you 2 numbers at one frequency, at one spatial frequency, and they give you a limiting resolution. We pointed out earlier, this is sort of meaningless, but they like to publish it. None of them, no camera manufacturer that I've looked at in the most recent brochures publishes anything about vertical resolution. Now, here's the way it works. This is, again, typical. I've just sketched in a curve of a typical 2/3 inch camera, horizontal. This is the camera. Now you put in you digitize it, you put in the digital filter, and that digital filter will lop it off. So you lose all of that. And this is what the camera is delivering. I'm just reproducing, cleaning up a bit here. This is what the camera is capable of. You hang a lens on it, and the lens has 75% at that frequency, has 60%, as I pointed out, at Nyquist. So this is a good 2/3 inch lens. You multiply that by that, and bingo, you get 45%. So that's what the camera manufacturers are actually telling you. It's their characteristic multiplied by a typical high-definition lens, and they will quote that number and that number. But it tells you nothing about that curve. It tells you nothing. It's been suggested by some, by the way, that another way to do is to say, let's quote all cameras at a 30% MTF, go out to the curve, and then read off here and say that's a 900 line resolution camera. Yeah, it's still a spot measurement. It's not really telling you much. The only way to distinguish between different manufacturers' 2/3 inch high definition cameras, because one of them, they may have identical numbers here and here, but the belly of their curve can and probably is different. So making 4 spot measurements at 200, 400, 600, and 800, like this is what they quote, but with a test chart, put a lens, pick your lens, hang it on camera A, make 4 measurements, hang it on camera B, make 4 measurements, camera C, make 4 measurements, and you will then be able to see the lens camera profile variations. And you can see that, oh yeah, maybe one camera has what Mr. Shade would have liked, a little bigger belly. Now whether you'll see something striking in the imagery, probably not, but you would like to get the best when you're going to spend a lot of money on these lenses and cameras. It's also a way of looking at those 1920 by 1080 digital cameras, but are using subsampled imagers. You measure that profile and you'll quickly see the curves are different. As you go down in your subsampling, you will get less MTF. Note that they are all delivering the bandwidth of high definition. So they're all bona fide high definition cameras, but this one is distinctly going to be sharper than this, and they're both going to be sharper than that. Now, if you see this by itself, and you've all picked up an HDTV camcorder and been sort of amazed at the pictures, there's something about high def, you just love it the minute you see it, and they're valid. But if you put them side by side with something that's got a little more beans, you'll start to see the differences. And of course, there's always a big difference in cost between these and these, so it's an issue of cost performance. And it was that way with motion picture film, which is why we had 65mm Super 35, 35 Super 16, 16, cost and performance. It's the same in the digital domain. It's a hierarchy.